Hello dear students, let us continue our discussion on the first unit. So we had seen in the last lecture that convex polyhedron is a convex set, and then we had seen what is called a convex hull. So in convex hull means there is no restriction on the number of points in the underlying set. Okay, so if x is a set, x is a subset of e to the power n, okay, it may be finite or infinite. If x is finite, then convex hull of x is nothing but the convex polyhedron generated by the points of x. Okay, but if x is infinite, the convex hull, this Cx, that is the convex hull of x, okay, of the given set x. Convex hull of x is the, what is this? Is the set of all convex combinations. So by definition itself, convex combination means of a finite number of points. Okay, of all is the set of all convex combination. Convex combinations of the points of x. Okay, points of x. Okay, and additionally, I had written taken finitely many at a time. Okay, taken finitely many at a time. Okay, so this one I had already written, and I had asked you to show if this Cx is a convex set or not. Okay. So I hope some of you have tried, so let us actually do it. Show that, or you can write it as a theorem. I don't know, it's all the same. You write it as a theorem or what. Okay, so show that a convex hull is a convex set. Okay. So how to show this? Proof or solution is this. So let x be a subset of e to the power n, and Cx be the convex hull of x. Convex hull of x. Okay. So we have to take 2 points from Cx and show that it's convex combination of those 2 points is a point inside Cx only. Okay. One more thing you try to observe, what about empty set? Is phi a convex set or not? Phi is convex or not? Empty set phi. So this actually is a trivial result. Means we need to agree that phi is convex, because if we say that phi is not convex, then we need to find 2 points inside phi, so that the straight line joining them is not inside phi. Okay. But that is never possible. We can never find 2 points inside phi, because phi is an empty set. Okay. So we cannot argue that phi is not convex. Okay. So phi has to be convex. Okay. So this happens always for empty set. Empty set almost satisfied every criterion. Okay. Empty set is convex. In analysis, you will see empty set is also bounded. Okay. Lots of things are there. So the argument is similar, something similar. We cannot show that it's convex. Okay. So there is only one option. It has. We cannot show that it's not convex. So there is only one option, that it is convex. Okay. So here we don't need to mention about phi and all. Okay. So let us take Cx be the convex hull of x, and that say x comma y belong to Cx, or I had started with your a and b, no? Okay. Let us do it with we will do it with x and y. X comma y belongs to Cx, be any points. Okay. Be any points. Okay. What I have to show? I have to show that lambda x plus 1 minus lambda y, this is also inside Cx. Okay. So, since x and y are elements of the convex hull of x, so how will they look like? Okay, that is what we have to identify now. So, x will be equal to some summation of I goes from 1 to say r of x, lambda I or alpha I. It's easier to write alpha I xi, okay, for some xi is for some xi I goes from 1 to up to r in x. Okay. So, what are the points of Cx? Points of Cx are just convex combination of the points of x. Okay. So, here small x is a point inside Cx. So, Cx will, x will look like some convex combination. Okay. So, it will look like something like summation I goes from 1 to r alpha I xi. For some xi's I goes from 1 to r in x, and 0 less than or equal to alpha I less than or equal to 1, comma summation of, this is a convex combination. Okay. So, summation of the scalars has to be 1. Okay. And the scalars should lie between 0 and 1. Okay. Also, y will be something like summation I goes from 1 to say s of beta I x yi. Okay. It may not be xi's. Okay. It may happen that some xi and yi are equal. That's a different thing. Okay. So, means y is a convex combination of some points of x. Okay. So, let us take those points as yi. Okay. So, for some yi I goes from 1 to up to r, okay, in x, and 0 less than or equal to beta I less than or equal to 1. Summation I goes from 1 to s, oh sorry, this is s, beta I, this is also equal to 1. Okay. So, these conditions are satisfied. Now, I have to show that lambda x plus 1 minus lambda y, this is an element inside Cx. Okay. So, let 0 less than or equal to lambda less than or equal to 1. Okay. Then what happens? Then let us compute what is lambda x plus 1 minus lambda y. So, the proof is exactly similar to whatever we have done in the earlier lecture about convex polyhedron. Okay. So, here the difference is that you have different points here. So, this is actually equal to summation of I goes from 1 to r of lambda into this, lambda into alpha I xi, okay, plus this is 1 minus lambda into summation of I goes from 1 to s of beta I yi. Okay. So, this is nothing but summation I goes from 1 to r. I can take this lambda inside, lambda alpha I into xi plus summation I goes from 1 to s of 1 minus lambda beta I into yi. Okay. So, this is a linear combination of x1 x2 up to xr and y1 y2 up to ys. Okay. This is a linear combination of these two. Now, if I want to show that this is actually a convex combination, then what I have to do? I have to show that each scalar lies between 0 and 1 and the sum of all the scalars is equal to 1. Okay. So, let us keep this one as 1. Now, 0 less than or equal to lambda less than or equal to 1, also 0 less than or equal to alpha I less than or equal to 1, 0 less than or equal to beta I less than or equal to 1, and since lambda lies between 0 and 1, so 1 minus lambda also lies between 0 and 1. Okay. 0 less than or equal to 1 minus lambda less than or equal to 1. Okay. So, if I multiply this, with this, then also it will lie between 0 and 1. If I multiply this 2, then also it will lie between 0 and 1. Okay. So, 0 less than or equal to lambda alpha I, this is also less than or equal to 1. And 0 less than or equal to 1 minus lambda into beta I, this is also less than or equal to 1. Okay. So, I have shown that the scalars are lying between 0 and 1. Okay. Now I have to show that the sum of the scalars is 1. Okay. So again, what is the sum of the scalars? Okay. So summation I goes from 1 to r lambda alpha I. Okay. This plus summation I goes from 1 to s of 1 minus lambda into beta I. Okay. So this is lambda can be taken outside. This is summation I goes from 1 to r alpha I plus 1 minus lambda can be taken outside. This is summation I goes from 1 to s of beta I. Okay. So it's lambda into 1. Summation of this is 1, already we have seen, and 1 minus lambda into 1. Okay. So this is actually equal to 1, right? Thus 1 shows that lambda x plus 1 minus lambda y is a convex combination, of x1 x2 up to xr and y1 y2 up to ys. Okay, this is a convex combination of this, right? So therefore lambda x plus 1 minus lambda y, this belongs to Cx. Okay, because anything that is a convex combination of the points in X, that is a that belongs to Cx. Okay, so for all xy inside Cx, we had started with arbitrary elements Cx and 0 less than or equal to lambda less than or equal to 1. Okay, so for this, right? So this convex hull or Cx is a convex set. It is a convex set, right? Okay. So this we have shown. One more thing that I had asked you to verify is whether the union of two convex sets is convex or not. Okay, so that is also one result. Another theorem is, we had done it for two sets, that intersection of two convex sets is convex. In fact, this is true for arbitrary intersection. Okay, so let us write the theorem also. Arbitrary intersection of convex sets is convex. Okay, means you take any collection of convex sets, their intersection is going to be convex. Okay. So for that, so remember one thing, the space e to the power n, this is always convex. Okay, because whatever points you take from e to the power n, their linear combination or convex combination is always inside e to the power n. Okay, it doesn't go outside. That is by the very definition of this e to the power n, the vector space properties. Okay, so from there itself it follows e to the power n is always a convex set. Okay, so e to the power n is always convex. Okay, so please remember this, convex. Okay, this is a whole set. So whatever points you take, whatever linear combination or whatever type of combination you want to do, you will ultimately end up with points in e to the power n. So e to the power n is always a convex set. Okay, no problem. Okay, so arbitrary intersection of convex sets is convex. Okay, so how do I do this? So let say C equal to some, so we need to take some indices. Okay, so let C equal to say A, or yeah, let us take this as this one. Let x equal to collection of Ci such that I belongs to capital I. Okay, be any collection, or yeah, any collection of convex sets sets, where what is this capital I? Capital I is an index set, set. What is an index set? It gives us the indices. Okay. Say I write something like, say usually when we say that let us take 5 convex sets. So what we do, we write it as something like C1, C2, C3, C4, C5. Okay. So this is a collection of 5 convex sets. So how do I write it in a short form? It is the collection of Ci such that I goes from 1 to up to 5. Okay. This way we write. Okay. Or we can write it this way, Ci such that I belongs to this set 1, 2, 3, 4, 5. Okay. So this, for this particular collection, this 1, 2, 3, 4, 5, this is an index set. Okay. So means we are denoting the sets one by one by taking the indices or the labeling. Okay. We are labeling it using this 1, 2, 3, 4, 5. Okay. So that is the thing. So in particular we use for if the finite set is finite, then we use the labels 1, 2 up to 5. Okay. But it's not necessary. You could have labeled it something like this also, C root 2. Okay. C say pi. Okay. C E. Okay. So in that case the collection will be something like Ci such that I belongs to this root 2 pi E. Okay. So this is the index set. Okay. In particular or in general, the index set may be infinite also. So in that case, say something like this. Suppose for each real number I get a convex set. Okay. For each real number I am getting a convex set. Okay. So in that case I may write this collection as Ci such that I belongs to R. Okay. Right. So here the index set is R. So it's an infinite collection of convex sets. Okay. Right. So that is the thing. So this I may be empty also. If the index set is empty, then the intersection of the empty collection means we get an empty collection of convex sets. Okay. So that is always convex. If we take the intersection of empty collection, we get the whole set. Okay. So that is also a convention. So where I is an index set. So if I is an empty set, then the intersection is equal to X. Okay. So that is also a convention actually. I mean intersection of empty collection, right? Intersection of Ci such that I belongs to capital I. If I is equal to phi, then this intersection is nothing but whole set X. Okay, but it's quite confusing because you have not taken any sets itself. So how intersection comes out to be the whole set? Okay, so this also follows from this logical argument. So suppose we take an element inside capital X. If it is not there in this intersection, that means what? X doesn't belong to intersection of Ci such that I belongs to capital I, right? So X is not there in the intersection means X is not there in at least one of the sets. Okay. So there exists an I inside I such that X doesn't belong to the Ci, but this itself is not possible. Okay, this is not possible. Why? Not possible as I is empty set. Okay, not possible as I is equal to phi. Okay, right. So that means if we take an element inside this whole set X, okay, then oh sorry, what did I do? This is actually arbitrary collection of sorry this X is equal to the collection. Okay, so this intersection if I is phi, so this intersection is actually the Euclidean space e to the power n. Okay, so if we take e to the power n means the whole set means Ci's are subsets of e to the power n, right? So if we take the empty collection of Ci's and then take the intersection, that is going to be e to the power n. Okay. So this follows from the logical argument that if we take any x in e to the power n, then x doesn't belong to this. If x doesn't belong to this, then what happens, there exists some I in capital I such that X doesn't belong to Ci, but this is not possible as I is already empty. So that means X cannot, it is not true that X doesn't belong to the intersection. So X has to belong to the intersection. That means every point of this e to the power n belongs to the intersection. Okay. So this is one thing. So the intersection of empty collection is always the ground set or the superset, the universal set that is under consideration. Okay. Intersection of the empty collection is universal set. So here the universal set is e to the power n. Okay. So let X equal to Ci so that I belongs to capital I be any collection of convex sets where I is an index set. Convex sets in, let us write that part. Okay, in e to the power n. Okay, where I is an index set. So if I is equal to phi, so just we don't need to write those details. Just write this part. If I is equal to phi, then this intersection I belongs to capital I, Ci is equal to e to the power n. Okay, which is convex, right? So let I not equal to phi, means we start with a non-empty convex set. Okay, right? Okay, so and then we take convex sets in the intersection from here. Okay, so it may happen that the intersection is also phi. So if intersection I belongs to I, Ci equal to phi, then it's convex. Then it is convex. Okay, it is convex. So empty set is a convex set. So let us also take intersection I belongs to capital I, Ci is not equal to phi. Okay, let this not equal to phi. So in the proof for intersection of two convex sets is convex, you may also mention this part. If A intersection B is phi, then phi is a convex set. Okay, probably I did not mention, I missed that part. So let intersection of this is not equal to phi, and so we have to take two elements inside this intersection. Intersection I belongs to I of Ci. Okay. So then we have to show that lambda x plus 1 minus lambda y is in this. Okay. Also let 0 less than or equal to lambda less than or equal to 1. Okay. Now x comma y, they belong to what? They belong to intersection I goes from 1 to means I belongs to I of Ci. This implies what? X comma y belongs to, so if something is there in the intersection, it means that it is there in every member of this collection. Okay, so x y belongs to Ci for all I belongs to capital I. Okay, but each Ci is a convex set. Okay, but each Ci is a convex set, So what will happen? This lambda, for this lambda x plus 1 minus lambda y, this is also inside Ci for all I belongs to capital I. Okay. So from there we see that lambda x plus 1 minus lambda y, this is an element inside the intersection. Okay. Right, because this is an element in every set Ci. Okay, so it's there in the intersection. So we have shown that this is actually a convex set, right? Thus lambda x plus 1 minus lambda y belongs to intersection I belongs to Ci. Okay, for all x y inside this intersection I belongs to I, Ci, and 0 less than or equal to lambda less than or equal to 1. Okay, so therefore this is a convex set. Intersection I belongs to I, Ci is convex. So in any intersection of convex sets is convex. Okay, so this is what we have proved. So it's not that difficult. The symbols are probably new to some of you. Yeah, so this is the thing. Another result that I probably missed was this, the intersection of finitely many convex sets. We have already proved it for arbitrary intersection. That actually implies that its intersection of finite number of convex sets is convex. Okay. So, so I give it to you as an exercise. Okay, exercise. You try to show this. If by chance in exam it comes that show that intersection of finitely many convex sets is convex, then you have to do it. Okay, you have to do it separately, independent of this arbitrary intersection. Okay. So intersection of finitely many convex sets. Intersection of finitely many convex sets. Finitely many convex sets is convex. Is convex. Okay. So that you can do. So for that, what you will do? You take let C1. So since it's a finite collection, we can always take the indices as natural numbers. Okay. C1, C2 up to Cn. Okay. Be convex sets. Convex sets where convex sets in say e to the power n. Okay. So let say something like C equal to intersection I goes from, so here I will write intersection I goes from 1 to n Ci. Okay. So we have to show that C is convex. Okay. So if C equal to phi, it may happen the C is phi, then it's convex, then C is convex. Okay. So let C not equal to phi. Okay. And x comma y belongs to C. Okay. And then you just proceed. Okay. Whatever we have shown, you take one lambda which lies between 0 and 1 and show that lambda x plus 1 minus lambda y is an element in C. Okay. So I hope you can be able to do it. Okay. Please do it yourself. Okay. Next we have this justification that the union of two convex sets is not convex. Okay. So let us see that. So before that, let us try to show this one. So in while doing this convex sets, I had shown you in diagram that this say this circle. Okay, this circle is a convex set. Means the circular disc. Okay, sorry, the circular disc actually it's a convex set. Okay. So this I had told you verbally, okay, but we had not proved it. Let us try to prove it now. Okay, say something like this: the interior as well as the boundary of the circle. Okay, so a disc, circular disc is a convex set. So show that this set, the set of all those x y, say S equal to set of all those x y in E square. So let us first do it for E square. This is a such that this happens. Such that x square plus y square is less than or equal to say some number, say 5. Okay, so this is a circle, a circular disc. So that the circular disc this with center origin and radius root 5. Okay, and radius root 5 is a convex set. Okay, is a convex set. Right. So how will you show this? So we have to take 2 points inside this circular disc and show that the straight line segment joining those 2 points is also inside the same set. Okay. So let us take this 2 points x1 y1 and say x2 y2 belongs to S. Okay, be any 2 points. Okay, so then what will happen by the given condition x1 square plus y1 square, this is always less than or equal to 5, and x2 square plus y2 square, this is always less than or equal to 5. Okay, this is already there. Now I have to find out what is lambda x plus 1 minus lambda y. Okay, so let 0 less than or equal to lambda less than or equal to 1, then what is lambda into x1 y1 plus 1 minus lambda into x2 y2, okay, y2. So this is actually equal to lambda x1 plus 1 minus lambda x2 comma lambda y1 plus 1 minus lambda into y2, okay, this set. Next, if I want to show that this point is inside S, then what I have to do, I have to show that this x coordinate square plus y coordinate square is less than or equal to 5, okay. So let us compute that. So now this square lambda x1 plus 1 minus lambda x2 square plus lambda y1 plus 1 minus lambda y2 square, okay, this is what this is equal to. If I take this lambda square common, it's lambda square into x1 square plus y1 square plus I take 1 minus lambda square common, it will be x2 square plus y2 square plus 2 into lambda into 1 minus lambda, this will also be common, multiplied with x1 x2 plus y1 y2, okay. So now using the earlier this inequality, we can always write this is less than or equal to 5 lambda square, because this quantity is less than or equal to 5, okay. This is also less than or equal to 5 into 1 minus lambda square, okay, plus 2 into lambda into 1 minus lambda. What about this x1 x2 plus y1 y2? That also we can write less than or equal to x1 square plus x2 square by 2, okay, this plus y1 square plus y2 square by 2. How I have written this, you just see, this is a very standard inequality, a minus b whole square, this is always greater than or equal to 0, right. So from there a square plus b square minus twice ab, this is greater than or equal to 0. So this is ab will be less than or equal to a square plus b square by 2. So whatever be the numbers a and b, their product is always less than the average of the a square and b square, okay, average of their sum of squares, okay. So this is satisfied. x1 x2 I can always write it as less than or equal to x1 square plus x2 square by 2, okay, and this also we can write y1 y2, this is always less than or equal to y1 square plus y2 square by 2, okay. So ultimately this quantity, and here I will write so again I will write less than or equal to, because it is 5 lambda square plus 5 into 1 minus lambda whole square plus 2 into lambda into 1 minus lambda, and what is this x1 square plus x2 square, I can just simplify them, I can just rearrange them, okay. So let me write one more step here instead of skipping the steps. Here I will write one equality and I will just combine these things together, x1 square plus y1 square by 2 plus here I will combine x2 square plus y2 square by 2, okay, this quantity, and then I can write this is less than or equal to, so we already have x1 square plus y1 square less than or equal to 5, okay. So this 5 into lambda square, 5 into 1 minus lambda square plus 2 into lambda into 1 minus lambda, okay, into 5 by 2 plus 5 by 2, okay. So this is actually 5, okay. So if we just simplify this now, so it's 5 lambda square plus 5 into 1 minus 2 lambda minus lambda square, okay, plus lambda square, sorry, and this is 2 into not 2 into 5 into 2 10 into lambda minus lambda square, okay, this one. If we just simplify this, if you see nicely, 5 lambda square plus 5 lambda square is 10 lambda square, it cancels out with this minus 10 lambda square. 5 into 2 5 into minus 2 lambda is minus 10 lambda, that cancels out with 10 lambda, okay. So ultimately you are left with 5 only, okay. So what I have shown, this quantity x coordinate square plus y coordinate square, this is less than or equal to 5, okay, this is already we have shown. So that means this is a point inside the circular disc, okay. So this is a point inside the circular disk. This lambda x1 y1 plus 1 minus lambda x2 y2. Y2 belongs to S. Okay, so therefore S is a convex set. So the same thing will hold if instead of 5 you are given something like 2, 3, 4 or A square, B square, C square. Okay, the way of proving is exactly the same. Okay, so we have shown the circular disk is a convex set. Right. So now let us come to this or some exercises. Say is the set S equal to, say, xy belongs to our E square, such that y greater than or equal to x square. Is the set convex? Okay, so how will you check it? So for this type of question, what we will do, we will just plot the diagram of the region that is being given. Okay, so y greater than or equal to x square. So first of all, what is y equal to x square? It's a parabola. Y equal to x square is a parabola. Okay, so what type of parabola? It's a, if it is something like y square equal to x, then this is this way. Here it's x square equal to y, so it's the upward parabola. Okay, so something like this. So it's a parabola. Okay, and y greater than or equal to x square represents the portion of the parabola above this. Okay, so this portion is represented by y greater than or equal to x square. Because y equal to x square is here. So if we go above, then y will be greater than or equal to x squared. Okay, so we have to show that it's not a convex set. So solution is very simple. You take 2 points here. You take 2 points inside this collection. So the given set represents the shaded portion in the diagram. Okay, portion in the diagram. Okay, but it is not convex. S is not convex. So what I have to do? I have to find out 2 points inside this set, such that the line segment joining these 2 points doesn't lie entirely inside the set. Okay, is it a convex set or not? Okay, on this one. Okay, so here what happens? Is it going to be convex? Sorry, it's going to be convex. Okay, and S is convex. The other way it's not convex. Okay, here it is convex. We can show it actually. So how to show this? Let x1 y1 and x2 y2 belong to S. Okay, be any element, and 0 less than or equal to lambda less than or equal to 1. Okay, then what happens? They are elements of S. So y1 is greater than or equal to x square. Okay, x1 square, and y2 is greater than or equal to x2 square. Okay, so what about this lambda x1? Lambda into x1 y1 plus 1 minus lambda times of x2 y2. This is actually, if we just write the coordinates, it's lambda x1 plus 1 minus lambda x2, lambda y1 plus 1 minus lambda y2. Okay, so let us check whether this is convex or not. So let us check whether this is a point inside S or not. So it will be a point inside S if what happens, if this y coordinate is greater than or equal to square of this 2 of the x coordinate. Okay, so we can do it this way. Say now lambda into y1 plus 1 minus lambda into y2. Okay, this can be written as greater than or equal to lambda x1 square plus 1 minus lambda x2 square, okay, by this inequality, okay, since 0 less than or equal to lambda less than or equal to 1, okay. Lambda is a positive non-negative number, 1 minus lambda is also non-negative, so just we can apply this these two inequality, okay. So lambda y1 plus 1 minus lambda y2 is greater than or equal to this, okay, but I have to show that it is actually greater than or equal to the whole square, okay, whole square of this lambda x1 plus 1 minus lambda x2 whole thing square, okay. So I have to show that this is greater than or equal to the whole square of this, no? Okay. Okay, let us try it the other way. I think the other way it's easier. Let us take the square of this and then we'll try to show that this is less than or equal to lambda y1 plus 1 minus lambda y2. I think that will be easier because here from here we cannot proceed. I cannot write this is greater than or equal to this plus 2 into this, no? Okay. So let us do it in a different way. Let us do it this way. So let us go to the other page. Now let us find out the square of this, okay, lambda x1 plus 1 minus lambda x2 whole square, okay. What is this square? This is what this is equal to lambda square x1 square plus 1 minus lambda square into x2 square, right? And this can be written as plus twice ab, 2 into lambda into 1 minus lambda into x1 x2, okay. So again I can use that result, lambda square x1 square plus this I can write as 1 minus 2 lambda plus lambda square into x2 square plus 2 into lambda into 1 minus lambda, and then I can write this one as x1 square plus x2 square by 2, okay. This quantity x1 x2 is always less than or equal to this, okay. So this is equal to lambda square x1 square plus x1 square minus 2 lambda x2 plus x2 square, 2 lambda x2 square plus lambda square x2 square, okay, plus 2 cancels and here it's lambda minus lambda square, so it's lambda into x1 square lambda minus lambda square into x1 square, okay. Let me write it in one step, lambda minus lambda square multiplied with x1 square and plus x2 square, okay. So you see many of the things will get cancelled. See lambda square x1 square, from here it will get cancelled, lambda square x2 square it will also get cancelled, okay. So what is left is lambda into x1 square plus x2 square minus, here it's twice lambda x2 square, here it is minus plus lambda x2 square, so we will be just left with minus lambda x2 square, okay. So it is something like lambda into x1 square plus 1 minus lambda times of x2 square, okay. And this we can write is as less than or equal to lambda y1 plus 1 minus lambda y2, okay. Yeah, we have got it. So this follows from so this is 1, so by 1, okay, by 1, y by 1 as 0 less than or equal to lambda less than or equal to 1, okay. Here we are using this, lambda is non-negative, 1 minus lambda is also non-negative, so this is ultimately less than or equal to this. So this point satisfies that square of the x coordinate is less than or equal to the y coordinate, okay. So it's convex, therefore lambda times of x1 y1 plus 1 minus lambda times of x2 y2, okay. This is an element inside S, so therefore S is a convex set, okay. So this is a convex set, okay. What I actually wanted to give you an example is this set convex, S equal to set of all xy in E square such that y is less than or equal to what did I do? Yeah, y is less than or equal to x square, okay. Is this convex, okay. So if the question is this, you will see that it's not a convex set. It will be, so we can draw the diagram. Diagram will be this only, sorry, it's a parabola. Okay, so something like this, sorry, okay, so something like this, y less than or equal to x square, that means it represents this portion, okay, this portion of the diagram. So here it's not convex, okay, if you take the straight line joining 0 0 is a point in this region, and say 1 1 is also a point in this region, okay. So the line joining 0 0 and 1 1, this doesn't belong to the set, okay. You can take other examples also. Instead of 1 1, you can take something like minus 1 1, okay, minus 1 1. This is also a point inside this region. It lies on the boundary, okay. But if we join these 2 points, okay, then we get a line segment which is outside, okay. So it's not a convex set, okay. So that is the main thing. So let us write it nicely. Okay, so if we draw this diagram, this is there. Okay, yeah. So it's a parabola, and then we have to mark the region. Okay, this is the region. Okay, so solution, S represents the region. S represents the shaded region. Okay, the shaded region. Okay, and S is not convex. S is not convex. So we can just give one line justification. Say 1 comma 1, this is an element inside S, and 1 minus 1 1 is in S, but the line segment, so here is E square is just plain geometry, so we can just give the geometrical argument, okay, by the line segment joining 1 1 and minus 1 1 is not in S, okay, right. So this minus 1 1, say some point here, 1 1 is some point here, okay, and then we draw this line. So you just show this by geometrical argument, okay. This point is minus 1 1, this point is your 1 1, but their line segment joining these 2 points doesn't lie inside the set, okay. It may happen that means you take some point here, okay, and then you show that, yeah, this line doesn't lie entirely inside S, okay, that also will do, okay. You can take any examples, just you have to take points in such a way that if you join those points, it is not going to lie inside, okay. See, if I take these 2 points, it is lying inside, okay. So that is not helping us here. If a set is convex, then for any 2 points the line segment should lie, okay. So that is why if we are able to find at least 2 points so that the line segment doesn't lie inside the region, then we can say that it's not a convex set, okay. So similarly you will see this is not a convex set, sorry, this circle itself is not a convex set, okay. Circle, say S equal to set of all those x y such that x square plus y square is equal to, say, a square, okay. This is not convex. You take one point here, you take a point here, you take a point there, and then you draw a line, then it is not lying inside the set, okay, because the set here for the circle, the set is actually only the boundary, okay. For the circle, the set is only the boundary, okay. For a circular disc, the set includes the interior point also. If it is a circular disc, it includes these points also, okay. So circular disc is a convex set, circle itself is not a convex set, okay, right. So okay, we have extended a lot, so I thought of doing extreme set today, but we will not be able to do, so next day we will continue.